concerning coherence, let's talk about the concept of thread-level speculation. This is also known as speculative multi-threading, speculative parallelization. It's really two ways of looking at it are the same, really. One way is to say, I have a parallel computer, I can build that, that's easy. Problem is, I need programs to be written in parallel, either explicitly or ideally parallelized by a compiler. That's much better. But a compiler is not going to be able to parallelize things when a piece of code is input dependent. And this happens a lot in real code. What is this? I have a write and I have an assignment to array, to a vector array element A, but the index is g sub I, which is a runtime constant. It's a runtime value. I don't know. At the compile time, when I look at the code, I don't know what a g sub I is. Also, I don't know what h of I is. It's not a value that I can easily figure out. Therefore, I don't know which iteration, okay, for I, which iteration I'm writing to the value, which iteration I'm reading from the value, okay? And if I don't know that, then I have to do this in sequence. Otherwise, if I execute some iteration, 1 to 3 on one node, 4 to 7 on another node, the execution of iteration 4 on another node may happen before the iteration of 3 on a node earlier than that, and then I will get into trouble. Okay, so for instance, okay, let's say in iteration 3, so I'm running 1, 2, 3. In iteration 3, I wrote to a sub 4 on this node. But then I'm running in parallel, so iterations 4, 5, 6, I'm running iteration 4 at a physically earlier time, and I was reading from A4. Okay? Now, of course, in sequential semantics, this should be reading from this value that I just produced over here. But in physical reality, if I execute this earlier, I would be reading from an earlier version of A4, therefore executing incorrectly. And if the program is really like that, I know that I'm writing to A4 in the third iteration, reading from A4 in the fourth iteration, then at least I can try to do something. For instance, making sure iteration 4 is always executed in the same core that I execute iteration 3. So they will be done in order. But the problem is code is most likely to look like this thing that we show, that we don't know who's writing to what. Okay? So, what is thread level speculation? By the way, this happens a lot. And the reality is in the actual execution, this seldom really creates problem for parallelization. So the code is quite parallel, meaning the example that I just gave, the writing to 4, that doesn't happen very often at all. So thread level parallelization cannot be done with guaranteed correctness. Why don't we speculatively do it and somehow detect when we're wrong? If we're wrong, we somehow roll back, undo any damage, and proceed to execute a certain part of the code serially. You can do that. So that's one perspective, thread level speculation. Another is that let's say we have instruction level speculation. Okay? What do? We speculate across branches. We do branch predictions, right? And it turns out branch predictions have less than 100% accuracy. So if we speculate across maybe a couple of or a dozen branches, the cumulative probability that we're still on the right path is very low. Okay, So what do? Well, it turns out here is something that is possible. We may have a very unpredictable loop body, but the loop structure itself is rather predictable. So if I have code that's a loop, right? It has if then else in between. Let's get rid of this. And it's a loop. Okay, so this is 50%, let's say. The accuracy of that is 50%. So if I execute this loop in a conventional uniprocessor, I would predict this branch. Let's say I predict it's taken to the left, and then this is very easily predicted. It's a loop branch. I have high confidence, and I start to fetch the next iteration. I predict again. Let's say it's taken. Now I'm only 25% likely to be right, and if I'm wrong, I have to squash, right? But can we do this? Can we speculatively execute this one iteration? We say, I'm not going to predict this, but this is very easy. This loop branch is very easy to predict. So I'm going to essentially unroll the loop dynamically. So one iteration, iteration 0, 1, 2, and so on. But I'm not predicting that branch. I'm just going to execute it. And if it's wrong, I don't have to squash the next iteration. If I do something like that, then I am not speculating in a fine-grained manner. I'm speculating in a coarser grain, and that's what the thread level means, not instruction level, but a kind of a loop, okay? So, very common example. Have a loop, does something. Usually when there's a loop involved, you have arrays, and I want some iterations to be done on one core, another set of iterations to be done on another core, perhaps speculatively. I don't know that they're parallel, that I can execute these iterations at the same time I'm executing those iterations. But if I have the ability to unroll, to roll back, to undo what I did, then it doesn't hurt to try. I can try, and if I realize that there was no dependency that I violated, okay, then I already have the result of the program, and I'm faster. If I realize I was wrong, I violated some dependencies that I didn't know existed, too bad. I throw away that, and at least I still have the non-speculative version that was executing on the very first thread context. Okay, so how do we do this? Many papers have been written about it. We're just going to use one example. It's not necessarily the best example, but it's one of the earlier examples, and it's called multiscalar. And it's exactly looking at this structure that I was talking about. It's a loop. The fact that I will need to execute the next iteration is highly confident. But within each iteration, I don't know what it is. So I want my unit to execute this. Okay, one unit, core, execute one iteration, another unit, execute another iteration. Whatever the second iteration needs from the first iteration, we'll wait. I'm not going to speculate. And whatever doesn't depend on that iteration will be allowed to proceed. So that would be good. So how do I know who depends on what? Well, that depends on the code. Suppose I have the code. I can look at the code to say, well, there's a instruction producing register R1, and there's another instruction producing register R2, and so on. So I can create a mask to say, okay, these registers are being created from this iteration. No? I can look at it. If there's branch, I have to be conservative. I have to see what can possibly happen. So my create mask is the conservative maximum amount of update to all the registers that I will do. Okay, so I know that. This is for this piece of code. Now I can pass it on to another unit, the second iteration, if you wish. So cumulatively, I have, since this is the very first unit, then cumulative, that's my create mask. We know these registers, if anybody's reading from these registers, they better wait. So now I look at a second unit. Let's say it's not the same static code, and it's creating a different set of registers, 4, 5, 6. Fine. So now we know that from at this point, all these registers are being produced by an earlier thread. Okay, the cumulative mask is larger. So if I keep on doing this, and I will figure out what are the live outs. Okay, what are the registers that are still being written out and someone in future generation may read. And how do I wait for them? Well, I create reservation station. So if I'm executing in this thread, I will know that the thread mask handed down to me is this over here. So I will create reservation stations as if these are local instructions that's going to update register R1, R2, and R4. I'm just going to wait for them. Okay, so it's as if before my code, I have 3 fake instructions that says update these registers. Who's going to update them? Who's going to give me the value? It's this guy on the left-hand side in some future time. Okay, I'm just now creating reservation stations for them. So when this piece of code over here finished producing register R1, when? You have to be careful, not the first time, the last time, when we guarantee that no more update to R1 is going to happen, this is the last final update, we send this forward into the future threads. And all future thread will capture that, okay? And it will know, based on the accumulative thread, it will know, oh look, I'm not producing R1, so this is a pass-through. I need R1, 2, 4 for me, but I'm not updating 1, 2, so I'm using the R1, and I'm also have to pass through R1 to subsequent thread. So if you do that, you'll be fine. So how is this done in a real code? Here's an example. I believe this is alpha instruction set, but it really doesn't matter. We can roughly figure out what it is. This is your destination register, okay? The first, so load, it's a destination register. Okay, so you now see, we know what the create mask is. Okay, what's the create mask? 4, register 4 is being updated. Yeah, it's right there. It's possible. Is it, you know, we could go around the branch if not equal, can go around this. So we don't necessarily have to update 4. It's also possible that update 4 happens here. Okay, so we don't know, but it's possible. 4 is possible, 8 is possible, 17 is possible, 20 is possible, and 23 is possible. Nothing else is possible. Okay, so that's our create mask. You see that? And then when do we release a particular register? Well, the last one. If you look at this code over here, register 23, let's say. This is the last case. We're updating the register. So there's a bit associated with the code to say once you execute that bit, forward register R23. Same thing with that over there. Okay. Sometimes you have control flow, you know, that there may be a branch. We don't know which branch, whether the branch will be executed or not, so sometimes we may have to have a specific instruction added to say, you know, if we get here, we have to send R4, register 4 forward. So that's the idea. We want to do this, compiler can analyze this, we can create these bits, we can create the mask, and we can propagate that. Done. So now if I have a piece of code, I will put one thread on one processor, another thread on another processor, and so on and so forth, and they each have their own little reservation stations or mechanism to forward data, and I'm done, right? Yes? Am I done? No, far from it. The challenge is always memory. Okay? Register-based dependencies are easy. Why? It's written there. This guy produces register R8. This guy reads from register R7. Okay? For register-based dependency, the dependency is literally written into the instruction. You know where it is. You know who's doing what. Not so for memory-based dependencies. We don't know. We don't know the address. The address has to be computed on the fly, online. So who knows? Who knows what address, who's producing to what? Okay? So the idea is really just a brute force solution. It's not, you know, there's no simplification. You can come up with some optimization, but they went with full-blown, complete, brute force solution. They call it an address resolution buffer. This is really just load store queue on steroid. Okay, just a gigantic load store queue that takes into account that your ID, your order is really now two levels: your thread order, your thread ID, plus your instruction ID within that thread. Okay, so memory accesses are all prepended with a task ID just to give you a global ordering. Okay, so if you your speculative stores cannot be released because you might be squashed. So you have to buffer them. If you have a store and you are not the very first thread, too bad, you have to keep your store in some sort of a queue to be released. So when the thread becomes non-speculative, you can release it. That's when every thread ahead of you became got committed completely, then you become the new non-speculative thread. So when you issue a load, what do? Just like in the store queue. You go and search all earlier versions of stores to the same location. Okay, so maybe it's not there yet. Okay, then you speculatively use whatever is the latest version that you found. If no version whatsoever is found, go to the memory. And then when you have a store, you send to the ARB, and store searches in the future direction to see if any load has prematurely executed from my thread, from a different thread, from a thread following my thread. If any load has issued prematurely, then we squash. Okay, we usually just squash that entire thread to begin with. But you can selectively squash only after the load, but that's what you do. What if you run out of space? You squash. Anything that didn't satisfy you, you squash. That's the general idea. Okay, so once you have this, you now have essentially a out of order execution for lots of coarse grain concept called threads. Okay, and that is one example of thread level execution, thread level speculation, or speculative multi-threading. Okay, so now what do? You have all these L1s, you have an L2. Okay, that's sort of the shared global thing. Each line now has multiple versions available in their chip, because if I write to a memory location, I can write in my cache, and then I can read from my cache line. That's perfectly fine. I cannot write it to the globally shared L2 because I may be speculative. I can do this if this guy is completely done. Okay, so every read, we'll try to read it from its own cache line first. If it doesn't exist, I have to go forward, search to see if I have a version. I want to find the latest version that I can. And when I have a write, I have to search in the future direction and squash. Okay? So to be a little bit more careful about it, or more sophisticated about it, you should record producer and consumer versions. And why? Well, if I read, let's say I want to read memory address X, I don't find it in my L1, so I go, oh, and I found it was produced in T2. So I have to remember that this is from T2, thread 2. Now later on, if at this point in some execution sequence in the code of P0 or T1, actually it's called T1, thread 1, I have a write to X. And I do a forward-based broadcast to say, hey, I'm writing to X. Well, if I look at this and say, oh, too bad, I've read from someone already, then I have to be squashed. No, you read from a later version. You were reading from T2, so that's fine. If T3 later on sends you a write notice to say, oh, I just wrote to X, you look at your thing, too bad. I was reading an earlier, older version when I should have read from T3, and then you squash. Okay, so this is doable. And a lot of proposals have been put forward about this detailed design. Probably about 1,000 papers have been written on this topic. Maybe that's a slight exaggeration. Maybe it's 300. But lot has been put in. Okay, and it's really just either trying to help parallelization, because strict parallelization is too difficult. We have hardware support, so it makes parallelization a little bit more relaxed, a little bit more speculative. We can do that, or this is about, we've run seemingly to the end of so-called ILP speculation. Can we do something to keep on using the available transistor budget? So that's TLS. Again, it's not something that's been commercially adopted in any real sense. There may be elements, very, very small amount of the element borrowed from the idea, but I don't think this is something that is completely useless. At some point, when we run out of lower hanging fruit, I think the processor vendors would come to use this. So that's all about the shared memory substrate, what I call the shared memory substrate. It consists of the concept of what is called cache coherence and what is not even in the domain of cache coherence, but in the domain of memory consistency. And then we realized that with those models, we can implement them in different situations: bus-based, snooping, directory-based. Okay, these are the implementation details. We will talk about synchronization in separate videos, so that's no longer true here. I forgot to change that. I recommend the Kueller and Singh textbook. There's a lot more detail. These are all the sections about these different concepts. The microarchitectural support that we discussed, they are described in literature, in papers. Again, that's on Blackboard. You already have those. Hardware manual, the alpha manual, is in Blackboard as well. And this concludes this whole part. And next time we move on to synchronization.